Thank you. Greetings, everyone. My name is Adam Kadlachik, and I'm not really going to talk about GPUs today, but rather of a phenomenon that we can observe from a laboratory, and I'll talk about some simulations about it. So, but to do that, I need to show you the phenomenon itself to understand it. So, okay. So first, I'm going to give you an introduction of this phenomenon. Then I'm going to show you how we reproduce it. I give a qualitative explanation of why it exists. Then, if I have the time, I talk about the measurements we did. And after that, I show you actually the quantitative theory and the simulations and all that kind of stuff. So as an introduction, first I'm going to show you a phenomenon that's quite similar to the one that we were observing. I'm sure many of you have heard about Newton's bucket, which is basically a bucket filled with water, and it is rotated around its axis, and because of centrifugal force, the water is pushed outwards, takes up a paraboloid shape, and yeah, that's basically it. It's quite an easy thing. Even Newton himself has tried it out. Now, what we do is different from this in only one way, which is that we do not rotate the whole bucket, only a plate near the bottom. So that means that we only rotate the bucket's bottom, the balls remain stationary. And from this, what we get is that while in the middle, the liquid will want to move with the rotating bottom plate, near the walls, it will want to stay stationary, and it's going to gain this quite weird shape. And of course, again, if you rotate it high enough frequency, then in the middle, the water will be pushed outwards completely, and it will have a dry middle. Later, we'll see why this is important. So what really is the difference between these two things, the Newton's bucket and our phenomenon, is this boundary layer that we see there, which I'm going to call delta. This is going to cause of a lot of interesting things. But let's see how this delta actually looks like. So here are the two buckets. They are rotating, and we have the liquid inside, and we're going to look at this part of the liquid, namely its tangential velocity. And what we see in the Newton's bucket case, that of course, as we go outwards, its velocity is going to increase linearly. While in our case, in the middle it's going to go similarly, but near the walls it's going to drop down quickly. It's going to have a velocity difference. If we plot this on a qualitative graph from the laboratory frame, we see that near the middle we see some kind of a solid body rotation, but near the wall at this delta boundary layer, we see a velocity shear. It's even more interesting if we look at it from a co-rotating frame, where again at this delta we see a faster flow velocity shear, and this velocity shear is going to be the reason that we see different and more complex shapes.
So would it mean that if you would have a superfluid, that it would be the same?
Well, I'm not sure about that.
Then you cannot get it to turn up.
Yeah. Okay.
So, but I didn't really show you any shapes yet, so I'm going to go ahead and do that. So I show you how we make this phenomenon. Here's a sketch about our measurement setup with the bottom plate, the cylinder, and the camera from up top. Here's the actual setup we use. We have a motor, transmissions to highest frequency output, we use cylinders for the bucket, and there's the rotating plate. And here is a video of the phenomenon we made, which is a bit, I don't like PowerPoint, but I think the main thing can be seen that the camera is looking at it from the top, and we see a rotating square. Now, you might ask if we can only make squares or not, and no, we actually could achieve circles, ellipses with two corners, triangles, and squares. In papers, you can read about pentagons and hexagons as well. I haven't read about a septagon so far, but I think that's plausible as well.
Excuse me, what is the number here?
N is the number of corners of these polygons. Yeah, so I talked about that these polygons exist because of this delta boundary layer, but I didn't exactly tell you how. So what we see here is a hydrodynamic instability. If you're not familiar with that, it is an example for that would be Kelvin-Helmholtz instability, which is when we have two different fluids with a relative velocity difference as seen on the simulation. And what happens is that these wave-like shapes start forming. Actually, you can sometimes see this phenomenon with clouds. There are really nice pictures on the internet of this. And now in our case, we do not have different fluids, only a relative velocity difference with this delta layer, but that is enough for us. So what happens here is that we have this velocity shear in the fluid, and let's say that small perturbations form spontaneously. And what happens is that I show this on this sketch, that we have here a flow, and because of the small perturbation, its cross-section decreases. And because of continuity, its velocity will increase, but on the other side, the velocity will decrease. And Bernoulli said that when something, a flow is faster, then its pressure is going to be lower. On the other side, it's going to be higher. So this perturbation will grow. And these will be these wave-like shapes that we see later. Okay, we have waves. How do we have polygons from those? Now, in these polygon vortices, we have these waves basically, but do not forget that we have a periodic boundary conditions. These waves basically go in circles. So what happens is that only those wavelengths are amplified, which fits on this circle round number times, integer times. And this is exactly what we see here as a sketch of that we have these waves that fit on this circle, and these are the polygons that we see. Another way to phrase this is that these waves interfere with themselves, and we see their superposition. So this is the reason that we see these polygon vortices. Yes, so during our measurements, we made measurements on what kind of parameters, how affect these polygons. By that I mean with different initial conditions, what kind of corner numbers we got. And I think I have a bit of time to talk about this. So we made a few phase diagrams of different initial conditions, like different radii of the bucket, frequencies, and height of the liquid. And yes, we can draw some conclusions from this. What I really want to say is that these experiments are quite reproducible. So if you give the same initial conditions today and tomorrow, you get the same polygon. Okay, so now on to the quantitative theory. The equation of motion would be, of course, Navier-Stokes, which writes down fluid dynamics. We really can't wait for an analytic solution because this is, of course, a turbulent flow. And the only way to really solve this would be to make a numerical simulation. And during our research, we really didn't have any experience with doing this kind of simulation. So we asked around what we should do. And we were told that we should try a program called OpenFOAM. And we got a computation time at the GPU lab of Wigner Research Center of Physics. And what we did is made a few simulations. Here are those. And the last one is really just a final simulation to try the program. But on the right side, we have a simulation which was meant to which are at initial conditions at which we should be seeing a polygon vortex, but we do not. And that is mainly because probably the mesh wasn't fine enough to actually see this, because in this kind of phenomenon, as I told earlier, small perturbations need to grow, and small perturbations cause the whole phenomenon. And if the mesh is not fine enough, we do not see these small perturbations growing. So what we would need to do is even make the mesh even more detailed. But even the above-mentioned simulation took days to calculate. So what we really see is that these numerical simulations are quite complex. They are hard to calculate, and because these small perturbations need to grow, if these small perturbations can't start because the mesh is not fine enough, we won't see the simulation properly represent this phenomenon. So what we later rather do is that we didn't run simulations, but we actually did the experiment itself, because it was it made a little bit more sense to actually do that than running simulations in this case. And what we wanted to do with our theory actually is to take a step back and look at this whole phenomenon from another angle and see if these polygons are actually similar to something else which can be written down with easier equations. And what we said, that what if we sit into this bucket and we are in a co-rotating frame. And what we experience is that we have a gravitational acceleration and a centrifugal one. And from these two accelerations, we can get a new effective G prime. And what if these polygon vortices are none other than water surface waves on a tilted surface with this effective acceleration? Now, to prove this, what we need to do is take the water surface wave dispersion relation. Water surface waves are waves that can exist, for example, in a pond or a bathtub. And this equation gives a correlation between the frequency of the wavelength, the gravitational acceleration, and the water depth. And what we did was that we modified this and tried it out for our polygon vortices. Here is the modified version where we have the frequency of the wave in the co-rotating frame, which is quite interesting that these polygons do not rotate with the same frequency as the plate near the bottom is rotated. Here you have the above mentioned effective G, the wavelength of the polygons at R mean, and yeah, what is the water depth? Well, we can't really say, because if we imagine which water depth should we be looking at. So what we do is give an order of an estimate for the order of magnitude as so. And what we did is we plotted the measured frequencies with the calculated frequencies and see how they line up. And we see that this is how they line up around a fitted line, which is slope is around 0.42. And from this, I will say that we can see that these polygon vortices can reasonably looked at as these water surface waves on this tilted surface. Now, I would like to summarize. So, yeah, I talked about polygon vortices, and they're caused by shear instability. And from our research, we get that these are quite similar to water surface waves on this tilted surface. Now, here's a picture of Saturn's North Pole, where I'm sure many of you heard that there's a hexagon. And if I know correctly, that is a quite similar phenomenon to this. That is caused by shear instability as well. I would like to ask, thank you for your attention.
Thank you very much. Any questions?
You mentioned this description with the co-rotating frame, but you also mentioned that each radius rotates at a different speed. So,
well, we took the mean of it. Well, basically, what we looked at is that we have this delta shear, that's delta boundary, and at the end of that, there is really the difference between the two velocities, and that was the position that we looked at, where we looked at this x velocity.
Further question? Is there any continuation of this work with us?
We don't know yet.
Okay.
Maybe.
Right. Okay. If there's no further remarks or comments, let's thanks Adam again. Very much.